Okay, let us start. Today, I will be discussing about sensors for energy harvesting and healthcare applications. In this particular lecture, we will be talking about RF absorbers, which are being used for healthcare applications, as well as one more use is there for energy harvesting for IoT, because IoTs are very small devices, and with the help of RF energy harvesters we can make those IoT or sensors with self-sustainable sensors by powering from natural resources such as RF energy. If I'm staying in the room, I have exposure of RF radiations from all over the places, because lot of RF devices, they are continuously radiating some sort of frequency at particular power. So my human body is exposed to different type of radiations. If the radiations are more than 1.6 watt per kg, that is not safe to the human body. We propose a technique that we can develop RF absorbers to suppress these radiations, so that our body or health is safeguarded from unwanted radiations. In this talk, I'll be talking about the design of RF absorber as sensor. We have designed these absorbers at 2.4 gigahertz and 1.6 gigahertz. And the sensor design is inspired from human sensing devices such as human eye, our skin as a touch is the sense, our ear, our smell, and the last is smell test. Now, the absorber characteristics, we'll be talking something about mathematical formulations, and then two different applications on harvesting, imaging, and detection. What is sensor? Sensor is basically a transducer which converts the energy from one form to another. These transducers can be made smart as well as self-sustainable using RF energy systems. Absorber is a device which absorbs EM waves and convert into some other useful form of energy. The EM waves absorbing material that acts as a lossy medium and offers attenuation. The energy is expended by oscillating molecules. Dissipating fields such as T or TM fields are excited. The electric and magnetic resonance is created at particular frequency. It has combination of FSS, dielectric substrate, and ground. These absorber can also be termed as HIS, SRR, and RAM, where HIS high impedance surface, SRR is split ring resonator, FS is frequency selective surface, and RAM is radiation absorbing material. When incident wave is placed on surface, the circulating current loops are formed into substrate due to coupling of strong resonance fields and proper impedance match. The incident waves is received by SRR, and it gives smooth passage to the substrate which is lossy in the medium, and because of that loss, it converts into heat, and the heat is termed as absorption loss. Basic parameters for an absorbers are that we want to have a resonant frequency for particular absorber. We want to have the reflection coefficient minimum as well as transmission coefficient minimum, the circulating current will offer a dielectric loss. If we talk about permittivity and permeability, we want to keep the index as negative, and that can be made possible if we are able to make permittivity and permeability negative. So these negative permittivity and permeability formulations can be developed, and this particular term can be coupled with the metamaterial absorbers. So whenever refractive index is negative, permeability is negative, permittivity is negative, then this type of material is artificially designed, and these materials will occur in terms of metamaterial. The main formulation for absorber using metamaterial is A stands for absorber, can be written as 1 minus S11 mod square minus S21 mod square, where S11 is reflection coefficient and S21 is transmission coefficient. We want the absorption to be maximum. That can only be possible if we can minimize the value of S11 mod as well as S21 mod values. The refractive index is negative, permittivity is negative, permittivity is also negative. Because of these negative values, the phase of signal advances as incident wave captured by FSS, and coupling due to resonance into dielectric causes circulating currents loop to form surface current from the radiations into the free space. An anti-parallel surface current distribution takes place between FSS and ground plane. The effect of dielectric loss and conduction loss is observed in the absorber. The impedance matching of absorber is done in such a way that we obtained this impedance equal to free space impedance, that is 377 ohm. The attenuation of EM wave takes place due to lossy substrate material and due to resonant electric and magnetic modes. These are also known as TE and TM mode. The earlier absorber used to have multi layers and bulky in nature, but because of invent of metamaterial, we are able to convert them into compact and very light, and not only in multi layer but in single layers. These metamaterial absorbers are insensitive to polarization as well as incidence angle. T mode and TM mode excitation is being developed using fluid ports. Reflection coefficient and transmission coefficient must be 0 to couple FSS received signal with the absorbing material. The SRR substrate must be backed with metal so that the impedance of metal is 0. The absorption is investigated in this particular model using E field, H field, and surface current density on T and TM mode. Strong absorption when input impedance is matched to free space impedance takes place, and SRR becomes resonant. This resonant feature gives extra coupling of feeds with the dielectric material, and the surface current is being formed. That surface current, with the help of SRR and ground plane, will be circulating into the substrate, and this substrate will offer the loss because of the material characteristics, and this loss can be made useful to convert using two different coefficient metals to extract DC as output. The other phenomena for converting this absorber into energy harvesting is that we can extract the incident surface currents to convert into the DC current using some rectification techniques. That energy can be used for IoT devices. So the absorption is investigated using E field, H field, surface current density on T and TM mode. Strong absorption when input impedance is matched to free space is being observed. incidence angle insensitive and polarization insensitive features are achieved. Impedance of SRR in parallel to substrate will form effective input impedance and absorber. Here in this diagram, if you will see that a FSS is on the top layer, the dielectric substrate is in center layer, and ground is placed in the bottom layer. So there are three layers: FSS, substrate, and ground, that can be represented with equivalent RLC circuit. So input in this three layer we will classify as ZFSS, Z material, and Z ground. And from these three layers can also be developed with CST model showing the fluent port 1, port 2, and FSS structure, and that can be replicated with the help of RLC circuit for realizing input impedance, and then the input impedance is matched to the load impedance. This RLC circuit can be verified with the RLC ADS simulator, and the ADS simulator will give us the reflection coefficient at the working frequency. Now, these absorption can be depicted with the help of E field, H field, and surface current plots, which we have taken from CST. These the fields has been also shown using animations, and this animation we observe that E field at 1.6 frequency, E field at 2.4 gigahertz frequency. Similarly, H field and J is also being shown using these animations at both the frequencies, and we have seen that the surface current is being observed at ground plane. The same thing is depicted with the animations, and we observe that the absorption phenomena is taking place, and these loop currents are being formed into the substrate. Now, the SRR can be of different shape and size. They form capacitance and inductive part. This capacitance length of the SRR will form L, and the gap will form capacitance. So this combination of L and C of any SRR will give me a operating frequency with the formulation F is equal to 2 pi under root LC. Now, in this CST model, we have shown two different SRR, and they are placed in such a way that one is resonating at 1.6 gigahertz and second SRR is resonating at 2.4 gigahertz. So, in energy harvesting, we can use the combination of these two, and the energy can be harvested. Further, these both frequencies are being combined into a common rectifier circuit, and we get output of rectifier circuit as a DC voltage, which can be used for IoT devices.